Hello. Okay. It gives me great pleasure to introduce our next speaker, Mike Stieff from the University of Illinois at Chicago. Mike received his PhD in Learning Sciences from Northwestern University. He, in fact, is the one person that introduced me to the whole field of relation between STEM education and spatial thinking. Before Mike received his PhD, he had received his master's degree in chemistry, and he's one of the few people working in this area who actually knows the STEM field in which we're trying to work. Most psychologists are not experts in the fields, but Mike really is, and it's made a tremendous difference. He collaborates with many, many people because of his wonderful collaborative skills, but also his knowledge of chemistry. Mike is currently living in Germany. Well, right now he's in Latvia, but before he came here, he was in Germany, on a Humboldt Fellowship, which is a very prestigious award that's allowed him to study for a year. He's published in the top journals of our field, and as I said, collaborates with so many wonderful people. So I don't want to take up any more of his time, so I'll give you.
Thanks, David, and thanks, Jurgis, for the invitation and to the organizers for the opportunity. This is actually my first time in the Baltics and to Latvia, and it's been a real pleasure to come a day early and sort of see the city of Riga and learn a lot about the history of the city and the country. I'm grateful for the opportunity and also to, of course, share my research with you. So what I'm going to be talking with you about this afternoon is the validity of visuo-spatial ability for predicting STEM achievement. And by STEM, I mean chemistry, because as David said, I'm a chemist by training. So all the examples I'm going to give you, I'll apologize, will come from chemistry, because that's the discipline that I know. And we'll learn a little chemistry together as we go through. David gave a really great talk this morning, and I think addressed a lot of the issues that are going to come up again here in my talk. And really the point that I want to make here at the opening is the types of spatial reasoning that mathematicians and scientists and engineers do is quite complicated. And what I'm going to try to show you is that sometimes it looks the same as what shows up on a psychology test, but often it does not look the same as what shows up on a psychology test. And the real challenge for us is to try to identify really what is the nature of spatial reasoning and spatial thinking in the STEM disciplines so that we can understand ways to improve it to address the problems of retention and achievement that David brought up. Okay, so let me first start off just with general definition of spatial thinking. I think this morning we talked a lot about spatial ability, and David touched on this quite nicely. But there's a report that's a little over a decade now that I think did a pretty good job of giving us a definition that's more comprehensive about spatial thinking beyond just spatial abilities. So the NRC report says spatial thinking, which is one form of thinking, is based on a constructive amalgam of three elements, which are the concepts of space, the tools of representation, and the processes of reasoning. It's the concept of space that makes spatial thinking a distinctive form of thinking. So if we look at the bottom, there are some various examples from STEM disciplines of what this might look like. And I think with regard to the spatial abilities, what we're talking about there is processes of reasoning exclusively around abstract geometric shapes. But what you can see from the various types of representations that are used in the STEM disciplines is that this gets complicated very quickly beyond what we see with the stimuli on the spatial ability measures. So whether you're reasoning about the surface of a three-dimensional object in mathematics, a block diagram in geometry, or a gear train in engineering, the things that we're asking you to do require a lot of content knowledge beyond just the abstract spatial reasoning skills that show up on those tests. What does this look like in the STEM disciplines? Surprisingly, across all of them, what you can see is we're asking learners to reason about how things change, spatial relationships change over time. And this shows up in very different ways with very different types of representations, but underneath it all, it's always about how spatiotemporal structures are changing dynamically over time. So here on the, my cursor, yep. On the left, a brake drum versus a pulley system. versus, again, a block diagram or a molecular structure from my own discipline. All of the representations look quite different from one another, but again, what we're asking our students to do is to think about what are these spatial relationships and how are they going to change over time. And we use different types of representations in order to do that because we can never see the objects either directly or on timescales that are meaningful to us. So really what I want to know is what is the relationship between a student's spatial abilities, their skill at interpreting these different types of diagrams, and their skill at predicting that change over time, which is related to the content of the domain. So we heard a lot about spatial ability this morning. I just want to recap a little bit because I want to talk about the validity of those measures for predicting whether a student's going to be successful in a STEM discipline. And David touched on these studies from the Project Talent 1960s data that I think have done a lot of shaping of the conversation about the relationship between spatial ability and STEM achievement. The diagram here comes from the 2009 paper by Y, Lubensky, and Benbow, and what they showed is when you take the Project Talent students and you break them into their stanines on their spatial ability, you can see that the percentage of students who go into the STEM fields differs dramatically based on what stanine that you're in. So up around the highest performance stanine, 8 and 9, you can see that up to 40%, 45% of the students in the 1960s chose to go on into STEM fields. As their spatial ability scores drop, they choose not to go into STEM fields. And this conversation has really shaped the argument around trying to train up spatial ability. If we already know that high spatial students are the ones who are going to go into the STEM disciplines, as David laid out for us, the logic goes, well, if you train up their spatial abilities, they will choose to go on into the STEM disciplines. I think David gave a nice argument about why that might or might not be the case this morning. So the question for me is, what do we do about this? How can we change this with regard to the STEM disciplines themselves, not necessarily through a pathway of training spatial ability uniquely? Okay, so David already told us this, spatial ability is not fixed. As I said, the argument that's been laid out is we should train up spatial ability in order to get them into the STEM disciplines. David also showed for us that there's some promise that if we could train up the spatial ability, if we could train up spatial ability through spatial training strategies, we might have the potential of increasing the representation of students in a field like engineering, right, somewhere on the order of a half a standard deviation. How do we do this sort of training? What does it look like? If you don't know this, it turns out that there's actually quite a few different spatial training programs that are out there, and I'm going to talk only about a couple of these here this morning and their predictive validity for improving the achievement of students in a STEM field. You may notice that across the images up there, you're seeing a lot of abstract geometric shapes because all of these spatial training programs have in common a focus on high degrees of practice with abstract geometric shapes in order to improve your spatial ability. And again, the logic goes, if we can do that, we'll increase the likelihood that you'll go on into the STEM fields. So I just want to interrogate a couple of these different curricula and talk about the data to date on how successful these spatial training programs are in terms of improving the representation of students in STEM, improving their achievement, and then explain to you a little bit about the research that we do showing in a post hoc way why some of the training programs today may not be as successful as we would have liked them to be. Again, the question that we're asking right now is how successful is spatial training? You may have already guessed that the direction I'm going with this is so far, it is not very successful. So taking students, putting them in a room, having them do high degrees of practice with generic geometric objects is not translating to higher performance in STEM disciplines. We'll talk a little bit about why that might be. Before we do that, though, let me just explain to you some of what I think are the most interesting success stories about these spatial training programs that give us some clues as to what the problem exactly is and how we try to unpack that in my lab around chemistry. So one of those pieces of scholarship comes from Miller and Halpern. This was published a couple of years ago, in which they took one of these curricula that I showed you on the previous slide. This is Cheryl Sorby's Introduction to Spatial Visualization curriculum, and put it into a university physics class. So to me, that this is actually a really good example of the type of research that needs to be done, because it's taking place in the real world with real students who are highly motivated to succeed in this class, and trying to layer onto it spatial training to see if we can increase the success of those students in a real world setting, rather than looking for their improvement on performance in a measure in one of our laboratories. So what they did is, these are students who are from a first semester university physics course. They attended a supplementary discussion section where they completed the Sorby curriculum, and this takes about 13 hours. Basically what you're doing is hundreds and hundreds of orthographic projection tasks. So drawing them in different ways, doing mental rotation on these objects as well. For those who may not be familiar with this, it's imagine you're looking at a 3D object from different angles. Can you draw it from those different angles? If we rotate it, can you identify the object? Lots and lots and lots of practice with this. So what they showed is, as David mentioned earlier, is that they were able to increase the spatial ability of the participants, these real life students who were in the physics class, so their abilities went up on spatial psychometrics. But the graph that I pulled from their paper here, these are their test scores from their class, and the blue group, the red group, and the green group are the three groups that were in our study. The green group is the interesting group here, because those are the only students who got the spatial training. And going from left to right, these are real live assessments that come from the physics class in terms of the types of quizzes and tests that they were given over the course of the semester. What you can see here is that they failed to find a universal benefit for the training group, that we were increasing their achievement on physics problems across assessments in the course. On a composite score, which is the bars that are first in from the left from your perspective, they did see a benefit of the training, but when you disaggregate the items on these physics tests, what's really interesting is that the training was only selectively beneficial to items like you see on the left up here, which are these kinematics problems. So taking the entire body of problems that the students are solving in the physics class, we don't get increased performance on all of them, but we do get increased performance from spatial training on a subset of the types of things that physics students are asked to do in a physics class. So for me, this raises a really interesting question. Really, what exactly is the role of these spatial abilities in helping students be successful in STEM? It's not just allowing them to move unabated through the STEM curriculum, but it's helping in very specific ways. And for physics, it seemed to be helping for kinematics problems. So that raises the question for me, what happens in chemistry, what happens in mathematics? Is it the same or is it different? One unfortunate note from this particular study that was done, though, is that they did come back and they tested them later in a delayed setting to look to see how much the training propagated into the future, and that's actually the set of bars that are on the right side there. They give them a force concept inventory test, which is quite a popular test of whether students understand the fundamental content, conceptual content of the discipline. And what you can see is when they came back 4 months later, there was no differences between the groups. They also tested them again on their spatial abilities, and they found that their spatial abilities had regressed back to being no different. So the training group was now performing equivalent to the non-training group as well. So once again, this raises the question of what exactly is happening with the training and how durable is it, both in terms of improving spatial ability as well as improving STEM achievement. Another successful example, I think, comes from Cheryl Sorby herself in a college of engineering, where this curriculum has been instantiated in several US universities. I don't know about other countries, but many universities, colleges of engineering in the United States have actually adopted the curriculum as a formal course in their colleges of engineering. Usually the way that this works is that the college will pre-test all of the incoming freshmen on their spatial abilities, again under the assumption that this is going to be a good predictor whether you will be successful in an engineering curriculum. If you fall below a particular benchmark on the spatial ability entrance exams, you get assigned to go into this supplemental course, which is a remediation course in spatial visualization, again following the same curriculum that we saw from the Miller and Halpern piece earlier. A big difference here, though, as I said, is this is an entire semester-long course. So it's not just a 13-hour supplementary instruction environment that's related to physics. The students are coming in and explicitly working together on the entire curriculum to try to raise up their spatial abilities. So in some sense, a much harsher treatment of the students than we saw in the Miller and Halpern example. Sorby and her colleagues have actually published several articles showing the success of this curriculum in terms of improving students' spatial abilities and improving their retention in colleges of engineering. And one of her most recent pieces, again, I think is a success story of general spatial training. What did she see? So what we're looking at here are regression continuity diagrams, and this is a common problem in education research when one is trying to do work in the field. Many cases we cannot randomly assign students to different instructional conditions because that's a violation of ethics. Students can't be mandated to participate in one instructional setting for the purposes of research because that's not why they went to college, and it's a bait and switch. So this is a really interesting statistical technique which allows you to compare under non-randomization conditions what would have happened to people who were in the intervention group if they were not in the intervention group. And the way to read these diagrams, if you're not familiar with them, is you can see the intervention group is the scatter plots on the left side of each of our charts, and the comparison group is on the right side. The dotted line that goes from the right side of the diagram to the left side is the regression continuity. So this is the continuation of the regression line from the comparison group into the intervention that gives us an idea of if you weren't in the intervention, what would have happened to you if you had all of the characteristics of the control group. So what you can see in both of those cases is that the discontinuity shows that for the comparison group, had they not gone through, or sorry, had they been in the intervention, they would have underperformed the students who actually went through the intervention. And note that all the intervention students are people who are lower on their spatial abilities, our x-axis there, because recall that when they arrived at the engineering college, they took a spatial ability test. They failed a benchmark and were told you must go into the intervention based on our curriculum requirements, but everybody else you don't have to. So if those students had been in there, here's what we would have seen, that their performance would have been under those of the people who were in the intervention group. So this is very promising, right? It shows that we, through general spatial training in the context of this engineering curriculum, we could predict that students are doing better. The only caveat I say about this is for those of you who spend a lot of time looking at scatter plots, you may notice that the spread is pretty big of our data points on both sides of that chart. And the fit of both of these lines turns out to account for less than 1% of the variance in the student's course grade. So there's a lot of other things that are impacting how students are doing in terms of their engineering grades, their calculus grades as we see posted here, and their overall GPA. And again, that raises questions for me. What are all of those other things that are actually predicting the outcomes for our students going through the STEM curriculum that are not their spatial ability scores with or without training? Okay, so those are two examples of people who have been doing spatial ability training that I think are good examples of success stories, but the success is not quite where I would want to see it as someone who's invested in improving the performance and the numbers of students who are going on into STEM fields. So what I want to ask is, what might be the problem here? Why is it the case that generic spatial training may not be improving the performance of students in as great, or to as great a degree as we would like to see it? So I bring back the pictures of the different types of representations that we know students are working with in the STEM disciplines. And then on the right side, these are the types of stimuli that you see showing up on psych instruments that measure spatial ability, going from perspective taking, which is the cube diagram up on the right, to a traditional meta rotation test in the middle, and then a paper folding test down on the bottom. Respectively, these are supposed to measure your perspective taking skills, your meta rotation skills, and then your spatial visualization skills going down. You may notice that they don't look a lot like one another. The representations that the scientists are working with and that they're asking the students to work with don't look very much like the types of items that show up on spatial ability tests. And first and foremost, this raises a question about the face validity of these types of tasks for comparison with the types of problem solving that we're asking STEM students to do. In essence, it would be the same as, you can't see my slides, can you? Why didn't somebody tell me? These are not changing anymore. Yeah, we don't seem to be changing. Sorry. Now they're changing. Thank you. I think. Yeah, this is really strange. Okay. Sorry, we'll go ahead. The slides that are here are not the same that you're seeing there. So we'll see what we can do around this. Hang on one second. Sorry. Okay. I think we are on the same page now. One of us might have to visualize what we're talking about, and hopefully it's me and not you. This was the slide that I was referring to before. So with reference to the types of representations that you can see on the left, those are, again, the diagrams that students from STEM disciplines are looking at. On the right are the types of items that come from spatial ability tests. Again, going from the top, perspective taking, mental rotation, and spatial visualization. Without question, all of them involve spatial information. But again, the semiotics of the diagrams that the STEM students are being asked to deal with are quite distinct from the generic spatial information they're being asked to reason with on a psych instrument, which once again raises this question of the face validity. So, it's the equivalent of asking the following, I think. On the left is a punch holes test. This is another test of spatial visualization. The stimulus you see there is quite canonical example of the types of things we ask students in the psych laboratory to measure their spatial ability. If that were a science question, I would argue this paper folding test, the punch hole test, should look something much more like this in terms of the complexity of what we're asking the participants to do around their spatial reasoning. And the shapes in this case, the triangle and the arc that you see, have some meaning to them, that they're not just generic geometric shapes, but instead you have to understand if a triangle is present, it means something different about the content. If an arc is present, it means something different about the content, and that comes not from generic spatial training, but comes from training in the discipline, which requires some level of expertise. So I want to throw a different perspective at you, and that is part of what we should add to the conversation is ways in which we can help students to take up the representational practices of the STEM disciplines, either with or without training of their spatial ability. So I've just thrown up here some common examples that come from organic chemistry. Along the bottom, you can see what we would call as a molecular model. This is showing the various transformations of different conformers that an organic structure can go through. Up at the right, this is a spectra that we would ask students to look at the Fourier transform and predict what the structure of a molecule would be. That's the structure in the diagram that's up on the right. So the Fourier transform is the same as the diagram that's up on the right, and arguably your ability to make that determination may not be dependent on your spatial ability as much as it is on your ability to understand the content of the domain. Simpler examples, I think, are what we tend to assume with regard to the space validity argument with regard to molecular structure, either things that are on the atomic level or things that are on the molecular level. Those look more similar to the sorts of things that you see on a psych spatial ability measure. Do you just know where they are in space? doesn't require a lot of content information, but what I want to argue with you about this afternoon is that the stuff that we ask students to do is actually more like the third picture and the bottom and less like the top two. So, in our lab, what we do is we try to understand how the relationship between students' activities and the instructional environments we put them in moderates and mediates the relationship between their spatial ability and the outcome measures. To be clear, I'm not saying that spatial ability is unimportant in terms of predicting the outcome, but what I'm going to show you hopefully is that I can tweak the relationship between spatial ability and those outcome measures pretty easily just by shifting the activity that students are engaged in or the instructional practices that professors are engaged in the class. So I'm going to show you 3 examples here. Those are strategy use, task features, and then tool use. And we'll just march through each of them to show you when we manipulate these different types of things, what happens to that correlation between spatial ability and outcome. So, first, strategy use. What do we know about how people solve spatiotemporal problems in the context of a STEM discipline? Turns out there's more than one way to solve these problems. It's not just about closing your eyes and visualizing spatial relationships. That is one way to do it, but another way that tends to be much more common around disciplinary practitioners are analytical ways that, as we heard Bob talk about earlier, tend to involve a lot of work with diagrams. So rather than generating mental images of things that we can't see, scientists, chemists in particular, spend a lot of time making drawings of the things that they can't see, and then their cognition operates on the drawings instead of operating on imagined structures. And these are what we would call spatial analytic strategies. We know that these are highly dependent on training. They can be learned, and so for us in our laboratory, the question we ask is, can we teach them? Can we see that they've been taken up, and what happens to students who are exposed to different types of strategies in terms of that relationship between their spatial ability and the outcome measures? I'll show you an example of what this looks like down here at the bottom. How many people have done organic chemistry? 2. Okay. So there are 2 sets of molecular diagrams on the bottom, set A and set B. They're in pairs. One set shows you the exact same molecule twice. The other one does not. Which is which? Is A 2 of the same, or is B 2 of the same? It's B that's 2 of the same, okay? B is 2 of the same. So I didn't give you any background information on how to do that, and only 2 of you raised your hands that you've been in organic. One, you need to know how to read the diagrams, right? So if you don't know how to read the diagrams, you're screwed. You can't solve the problem, okay? The way to read it is that anything that's on a straight line is in the plane of the screen. Anything that's on a black triangle is projecting out at you, and anything that's on a dashed triangle is projecting behind the plane. So that helps you understand a little bit about how chemists use these 2D conventions in order to convey 3-dimensional space. So once you have that down, it may look a little better in terms of making the decision about which is the same and which is the difference. I saw a couple of people doing the following. You were gesturing your hands like this, right? You were probably engaged in a mental rotation operation, trying to rotate one of the structures onto the other one to look for alignment. If they perfectly superimpose, they have to be the same thing. That's a perfectly fine way of doing it. That would be an imagistic way of doing it that you might expect relies on your mental rotation abilities. Turns out, though, that there's another way to do it, and this is the way that the chemists do it. So the chemists have developed a nomenclature system that allows them to annotate each of the ligands that are around the central core of the structure. You can see that here I've done it for you, and it requires a little bit of content knowledge in order to figure out which gets the 1, which gets the 2, which gets the 3, and the 4. Once they do that, they then draw a line going from 1, 2 to 3, and then they compare the lines, so the curves. Are the curves going in the same direction or in the opposite direction? If they're going in the opposite direction, it means that these are enantiomers. They're isomers of one another. They're not the same. That task only operates here on the chiral structures. The ones that are in the B, these are achiral structures. You may notice that those have 2 H's in them each. Everybody see that there's 2 H's? Because these are three-dimensional objects, the two H's in there generate a symmetry element in the molecule, cutting it in half. If that's true, any object that has a symmetry element, you can rotate it any way that you want. It will always be identical to itself. So when they look at symmetrical objects, they just instantly tell you those are the same. When they look at achiral objects, they have to make this decision around their nomenclature. So different ways that are trained up to do this in the context of a chemistry classroom. David already mentioned this. I showed several years ago that even chemists will use mental rotation to solve these sorts of problems in this classical paradigm, so I won't spend too much time talking about this. It turns out that angular disparity is related to your response time, whether it's a geometric shape or it's a molecular object for students. If we give this to chemists and they can't use their analytic strategies, you'll get this same result. This will show up as well. So it allows us to detect objectively without asking them, how are you solving these problems? Are you using your visuo-spatial abilities? Are you using your disciplinary strategies to solve it? So the study I just want to mention here before talking about the next one, again, to get at this question of predictive validity that we did is we did a real-life field experiment where we rolled out different types of strategy instruction in organic chemistry classrooms. We did this over a year and a half. Remember, we can't assign students to different instructional conditions. That's not allowed. But what we can do is we can change the instructional conditions for classes that they go into of their own choice. Based on the decisions of the instructors. So over a 3-semester sequence, what we did is we either trained exclusively analytic strategies in the classroom. The instructor talked only about those sort of diagramming strategies that I said. Or we trained imagery strategies. The instructor did not introduce any of those analytic strategies and instead focused exclusively on saying things like imagine it in your head, do mental rotation operations with the support of models. Or we did a third condition, which was combined. So the instructor did both of these things for the students. And before and after, we measured their strategy preferences, we measured their spatial ability, we gathered their prior academic achievement to try to understand if we expose them to different types of strategy instruction, what will that do in terms of their outcomes, and what will it do to the relationship between their spatial ability and their achievement. So here's what happens. Here's sort of what strategy instruction looks like on the right. I know it's a little bit of too much chemistry after lunch in the middle of the afternoon. Those are those chair conformers I was showing you earlier, those 6-ring structures. This is a way that analytic strategy instruction looks different from imagery instruction. So you may notice the numbers again up there on the diagram. So that analytic strategy would be numbering all the vertices, doing a spatial transformation, and then matching the alignment between the numbers. All of this takes place on the diagram. The imagery instruction looks like the little person in the bottom on the right, where we say things like, imagine you're sitting in the molecule and the molecule is changing around you. Here's how it would look. Here's how the molecule would update. The bar charts that you're seeing on the left, in terms of what we're doing here is trying to understand what are the strategies students use when they walk into the classroom versus when they walk out. So that is, white is your strategy bias when you walk into the classroom. Black is your strategy bias when you walk out of the classroom. And any bar that goes down means that from pre to post, you're actually giving up that strategy. Any bar that goes up means you're adopting that strategy more. White, in this case, are imagery strategies, so that's a bias to use this mental imagery. Black is a bias to use the analytical strategies working with the diagrams. So what you can see is that over the course of all 3 of these interventions that we worked with, everybody moves away from using imagery strategies. Everybody moves towards adopting these analytic strategies in direct response to the instruction that's being given them by their professor in their classroom. And to David's point earlier about whether spatial ability may be a bottleneck for students who are early in instruction, this may speak to that a bit in the sense that we know when students are walking into the class, they tend to privilege using mental imagery to reason about things that they can't see, and if that's the case, their spatial ability may be very important until they move away to adopt the expert analytic strategies by the end of the semester. So, what does this mean in terms of their performance on their course grade? What we saw is that in each of these classrooms, there was a difference between the sexes with regard to the analytic instruction and with regard to the imagery instruction, both in terms of chemistry task that asks specifically about spatial relationships as well as their overall course grade by the end of the semester. The interesting thing that we saw here is that with regard to the combined instruction, what we were able to do was to eliminate this sex difference. So if we're assuming that males tend to use more imagery strategies, males tend to have higher mental rotation abilities that lead them to use those strategies, our combined condition was showing that we could remove that bias that was leading to their selective advantage in the classroom, both on the spatial tasks in the classroom as well as on their course grade. You may notice that what we did is we raised the achievement of the women in the classroom without lowering the achievement of the men. So we didn't throw the men under the bus in order to make the women more successful, right? Everybody was successful in the combined instruction. And what we think we were doing here in that combined setting was helping the students to understand the relationship between the three-dimensional structures and the analytic strategies when they were put side by side in front of them. The most important takeaway from this, though, is a structural equation model we built showing that we can account for differences in performance between the sexes in the classroom only when we account for both the spatial ability scores as well as their strategy choice. So this is across all the semesters. And again, this goes back to this question of what is the relationship, what is the predictive validity of their spatial ability scores in terms of achievement at the end of a STEM class. You can see, so sex is dummy coded here. 1 is male, 0 is female, so positive coefficient means the male advantage, negative coefficient is a female advantage. Males tended to have higher spatial abilities, but females tended to adopt more spatial analytic strategies. In the end, when you account for both of these, what you can see is that the sex differences in achievement related to spatial ability before are explained away. So you have to take into account both the spatial abilities of the students coming into the class as well as the strategies they take up. It could be the case that if students don't take up those analytic strategies quickly enough, their spatial abilities will be more predictive in terms of the outcome measures in the class. Okay, so let's talk about task features. We don't do this sort of work anymore because it required us to manipulate what the instructors were doing, and that was a nightmare. Trying to control a professor's teaching practice is not an easy thing to do. So instead, what we asked was, could we manipulate the actual representations that are used in the curriculum? I'll talk about that quickly. And then could we manipulate the types of resources that we give to students to once again see what the relationship is between their spatial abilities and their outcomes? So here what we did is we asked the question, and this was a lab study where we brought students into our lab. If we asked them to do mental rotation of molecular diagrams or of molecular models, could we change the way the task was designed to, once again, affect the relationship between spatial ability and the outcome measure? So what does this look like? You can see both a molecular model up there as well as a diagram. The diagram is the same as the molecular model on the left, and we changed the axis of rotation. So in a common instructional setting, the textbook will always have the representations rotated in the picture plane. Always, always, always in the picture plane. It's the easiest thing to do. What we did instead was we rotated them out of the picture plane on the y-axis or on the z-axis, in addition to the common rotations on the x. And then we said you either do it with a molecular model, which gives you all the perceptual information of the 3D relationships, or we'll give you the diagrams, which, as I said earlier, requires a lot of content knowledge in order to read them. Okay? So what do we see? In the design here, we measured your spatial ability, and then we threw you into one of two conditions. You either got the molecular models or you got the diagrams, rotated around one of those 3 different axes. And you did a task like this. This is this classic Shepard and Metzler task. We just take the 2 representations and we rotate them. Same thing as I talked about earlier. They're either the same or they're different. We looked at your response time and we looked at your accuracy. How good are you at deciding whether these are the same molecules or different molecules? So what do we see? Okay. Again, this is a between subjects condition, so you either get the models or you get the diagrams, and they're rotated on the x, y, or z axis going from left to right. It turns out that the axis of rotation matters, but that's only true if you're working with the diagrams. It does not matter if you're working with the 3D models. Right? Why might this be the case? Well, it doesn't matter what direction you turn the model in, it's always going to be the same thing, and the perceptual cues are identical, right? But if you turn the diagrams around in different ways, the formalisms of the diagrams constrain the possible rotations that are allowable, And when you rotate them out of the picture plane, right, you're making the task actually much more difficult because it was designed by the chemist to be presented in picture plane rotations. And we can see that that affects your accuracy, right, and it affects your response time. So it's something about the representations themselves that are affecting your achievement here that may or may not be related to your spatial ability, and I'll show you in a moment why it's not related to your spatial ability. Okay? So how do we do that? We brought in a new crop of students, and now we did a within subjects design, exact same setup as we had before, but now we said everybody gets 2D diagrams, everybody gets 3D models, and everybody gets a new condition in which we're going to put a diagram next to the model and rotate them. And you have to tell us whether the diagram and the model are the same molecule or not, right? Hopefully you appreciate how hard this is, right? What we ask these participants to do. Once again, we're interested in their response time, we're interested in their accuracy. What do we see here? So it turns out, in the chart on the left, going from left to right, 3D model, 2D diagram, and the mixed representations. And remember, the same students see all of them, right? Everybody sees all of them, so you're actually controlling your own performance. Performance is highest when you're working with 3D models, it goes down a little bit when you're working with 2D diagrams, and it goes down a lot when we put a diagram next to a 3D model. So what does this mean to us? It's not about how good you are at rotating three-dimensional shapes, because you're pretty good at that, right? But when we change it to 2D diagrams, your performance goes down because you need to know something about how to read the diagram in order to do the mental rotation operation. And it goes way down if we give you a diagram and the three-dimensional representation itself, because this must be related to your competencies in identifying how the diagram and the 3D shape map onto one another. It's not how good you are at mental rotation, because remember, you're pretty good at rotating 3D objects, but when we take that away, performance goes down, so it has to be something else. It turns out we have a response time accuracy trade-off. It's the same. So notice that response time skyrockets when we put a diagram next to a 3D object, and that additional time has got to be the processing required to do the mapping between the different representations. Most importantly here in a moderation analysis, what we can see, remember, we measured their spatial abilities. Spatial ability is correlated to your performance as long as we're giving you the 3D models, but when we give you any 2D diagrams, the relationship goes away. So something else, what we argue is their representational competence, explains their performance when they're working with disciplinary diagrams that doesn't involve their mental rotation ability. Okay, last thing, tool use. So why is the previous study is important for us? Because, again, we don't have to mess with the instructors. Like I told you, they don't respond well to being told how to teach their classes. The task features tells us something how we can design curriculum materials in terms of the types of images we would put into text, the types of rotations we would want to show, the type of representations we would want to show participants. The type of assessments we would want to give them in terms of axis of rotation, something to think about from an instructor's perspective. But here, the last part I want to show you is that we can also manipulate this relationship between spatial ability and your performance by the tools that we give the students. So don't mess with the instructor, don't worry about the pictures in the book. What can you put in students' hands that would manipulate this relationship in interesting ways? It turns out that this discipline has a readily available tool, which is a concrete model. These are commonly used in instruction in chemistry, commonly used in instruction in many of the STEM disciplines. The model that I've shown you here, just so that we're clear, is the same model of a molecule that the diagram is. So the diagram and the model are both the same in terms of what they're trying to represent. They're just doing it in different ways. Unlike the 3D model I showed you before, this concrete model you could actually reach out and pick up, right, and do things with. So the question we're asking is, if we give you these models, how does it relate to your achievement? How does it mediate the relationship between your spatial ability and your outcome? So, what do we do in this study? Again, we brought them into the laboratory, measured them on their spatial ability, and then put them into one of 3 different studies. The first study, we put a model on the table in front of the students, said, here you go, right? Do with it what you will. In the second study, we put the model on the table in front of the students and we said, scientists use models like this in order to solve problems. You should use the model too to solve problems, okay? In the third study, what we did is we said, scientists use models like this to solve problems, and let me show you how you should use the model to solve these types of problems. So we actually did the spatial transformations for them, showed them how to align it with diagrams, how to make a decision, is it the same or is it different, and then gave it to them. Everybody clear on what we did? Okay. They went through that instruction, and then we gave them what we call a representational translation test, which looks just like this up there in the top corner, where we gave them different orthographic projections of molecules and said, here's one, make another one. Here's one, make another one, right? Not an easy thing to do, highly spatial in nature. Here's what happens. So I'm going to highlight just on this table 2 parts. Remember the 3 different studies, either we gave it to you with no instruction, we gave it to you and told you to use it, or we gave it to you and we told you how to use it. So that's study 1, study 2, and study 3, right, going from the top and bottom. Really all we care about right now is their drawing accuracy. Don't worry about their spatial ability or their experience. We can talk about it later if you want to. But here's the interesting thing that we saw. So there's 30 people in a condition, right? 30 people get the manipulative, 30 people are in a control comparison condition in study 2 and study 3. But the manipulative condition people, we can separate into 2 types of people. Those that actually pick up the model and use it the way that we told them to, and those who don't touch it at all, okay? It's on the table in front of them, but it's their choices whether they're gonna pick it up. We can't make them pick it up. We ended up calling this study the use it or lose it, because what you may notice in terms of their mean drawing accuracy, if you got a manipulative, you only gain a benefit in terms of your achievement on this type of chemistry task if you're somebody who picks it up, okay? You gotta pick it up and do rotations with it, or you're no different than the control group. And this is a little shocking to us because it means sitting a model on the table in front of the students is no different than having no model at all, right? In the control group, they had nothing, okay? That's also the condition that we tend to do in common business as usual and instruction is we pick up a model and we say, everybody look at the model that I have, look at the model that I have, it's helping you understand, and then I put it away and you take your notes, right? And you go on, you never actually get a model and I never show you how to use it, right? I just show it to you. That's our business as usual, at least in the US, of what we're doing. So you got to pick up the model to get a benefit from it, to get the boost. Okay, what's this have to do with your spatial ability, right? Remember again, what I'm asking is how can I tweak this relationship? It turns out that your use of the model mediates the relationship between your spatial ability, right, as measured by this battery of perspective taking, mental rotation, and spatial visualization, and your performance on these representation translation tasks, which are common disciplinary assessments. So what's this look like? Higher spatial ability people tend to use the model more. That's not so great because it means that the rich are getting richer, right? So they are already aware in some way of the affordances of using the model to help them. But using the model predicts how good you are at doing this type of translation, and it fully mediates the relationship between spatial ability and the outcome measure. So as long as you pick up the model, it doesn't matter what your spatial ability is. The only problem is you're more likely to pick up the model if you're a high spatial person. So the instructional, right, intervention that we're currently trying to think about is how do we get low spatial people to pick up the models. Okay, so it turns out that this translates into the classroom. I've been telling you about some lab studies. We went into real classrooms and did this as well. We went into 2 lectures and taught people how to do the translation just with diagrams. You can see that. Lecture 1 and Lecture 2 are taught by 2 different instructors. That's why they're separated. Lecture 3, we taught them how to do this use of the model thing, where we said from our study 3, pick it up, turn it this way, turn it that way. Here's a model, you do it too. Okay? And then we measured them on their content assessments in the class, including a quiz about this. And I just want to say really briefly, the model's condition in a real life classroom turns out to boost the achievement of the students in a class above and beyond the students who are in the lecture conditions. And those lectures, again, are up there because it's 2 different instructors. The Lecture 2 instructor is the same as the model's instructor, so it's not an instructor effect that explains this. So what we see in the lab directly translates to the classroom. Okay, so where have we been? Let me wrap up here. We talked about 3 different ways in which we can manipulate the relationship between a student's spatial ability and their achievement on authentic disciplinary tasks. Strategy use, modifying the task itself with regard to its presentation to the students, and the types of tools that we can give them. We see in each case that we can change the effect size, right? How much variance can your spatial ability explain your achievement changes as a function of these and likely others that we have not thought of yet. What does this mean for us as a take-home? So the point that I continue to try to make for people who are new to this area of research is STEM achievement is not equal to your spatial ability. STEM achievement requires much more than just what your spatial ability is. Rather, what I like to say is STEM achievement's probably in some way proportional to your spatial ability, and that may be time dependent, as we heard David talk about earlier this morning. But I want to also throw this up here, that probably the real equation is something like this, right? That your spatial ability is a function, or sorry, your STEM achievement is a function of your spatial ability, plus many, many other factors that we've not adequately identified yet in the student populations that are going through these. And at the least, the relationship between your spatial ability and your achievement, right, whatever that coefficient is, for sure, it's less than 1, and in many cases, it's 0, because these other factors are explaining the variance in your outcome more than your spatial ability is. Why is that? Right, to return to what I said at the beginning, the types of tasks that we give students on these spatial ability measures don't look a lot like what we're asking students to do in real life classrooms. So down there is an organic chemistry problem where we're asking students to understand how a linear structure wraps up on itself to form a steroid. I put forth to you that that really doesn't look remotely like a perspective taking task, right, or a mental rotation task that we would test students on, even though both of these types of tasks certainly involve reasoning about spatial information. No question at that. So I'll leave you with this. What's the root problem? I don't think the root problem is the kids. I don't think that the approach we should be pursuing is fixing their spatial abilities. I think the root problem is the way that we're teaching them. These are 2 images from the same classroom at the same university, 50 years apart. I put them in black and white, hopefully to try to hide from you the time points. You may notice that, right, one of them has a LCD projector, the other one has a chalkboard, but the structure of the classroom is the same, right? It's you sitting in seats, watching the person who's down in front of them, telling them everything. I think this is part of the problem. We're still continuing to use instructional practices that are not capitalizing on the resources students are bringing to the classroom. Per Bob's presentation earlier, we're constraining ourselves by old representational systems that may not be better or the best at helping students understand very complicated spatial relationships. We're forcing them into symbolic representations that actually make it harder to learn than it could be. And I just want to leave you with some, right, promises, because I don't think all is lost. I think people are doing really interesting things around how to teach spatial thinking within the context of a discipline. I don't need to mention, because David already told us, right, Bob Colvert's work around spatial thinking and GIS, I think, is a beautiful example of how to teach people to think spatially without worrying about whether their spatial ability scores are going up, but tying it directly to the content of the discipline. 2 other interesting examples, I think Kristen Garnier and Tim Shipley's work at Temple around teaching students how to make drawings is showing really promising ways of helping students understand how to do penetrative thinking in geology. Again, not making them better necessarily at penetrative thinking tests, but helping them understand if you draw, it may be easier for you to understand these spatial relationships in the context of the layers of the earth. And I think lastly, probably the furthest away from the conversations that are happening here, but to me one of the more interesting perspectives is Megan Bang's work about cross-cultural differences in the ways in which people talk about space and the ways in which they represent space. So for her particular work, she's interested in the achievement of Native American students in the United States in STEM disciplines. And one of the things that she's shown is that for this particular group of people, the way they talk about perspective is different than the way that a lot of Western countries do. And when they talk about ecosystems and food webs, the human is part of that system during the teaching activity rather than the observer outside of the system looking at everything from a top-down view. And these are, I think, interesting entry points that may raise the achievement of students from different groups as well as students from a majority group in whatever culture that don't rely on simply raising up their spatial abilities independent of the content or independent of the culture. So with that, I'll stop and say thank you once again.
Thanks a lot. So we have a couple of time for a couple of minutes, a couple of questions, a couple of comments. David.
This one's pretty specific. You might have to go back to the mediation thing. Like, was that the before slide? Because the bottom path was still highly significant. Like, stop, go back. So you say model use completely mediates the relation between spatial ability and translation accuracy?
In parentheses is the coefficient after the mediator is included.
Oh, okay. I thought that was the significance level.
No.
Okay.
No. So the correlation's 0.58 without the mediator. When you include the mediator, the correlation's nothing.
That is complete mediation. You're absolutely right.
Yeah.
I understand the representational system.
I should have put an NS in there, I guess. Yeah.
Any other question, comment, anything to add? If there are no other questions, then let's thank our speaker again. And now we are having the workshop part of the symposium, where the workshop with Professor Udall on the paradox of transferable lessons from spatial thinking will take place in this room, whereas the other workshop with Professor Kirke will take place in the small aula, which is just a couple of steps upstairs. And now one organizational announcement. After the